Okay, so here's the part 2 of our last section from Unit 3, radicals, higher order indexes, and then also we're going to look at rational exponents. So remember, rational is just a fancy word for fraction, okay? So the way this is going to work is if you have a fraction as your exponent, you're actually really dealing with a radical. So if you look at this example right here, if the nth root of a is a real number, then basically that nth root would be the denominator of an exponent where the numerator is 1. So if you have 1 over, in this case, n, that's the same thing as taking the nth root. So if you look at 83 right here, all this really is we're taking because the denominator is a 2, we're taking the square root of 36, which the square root of 36 is 6. Done. That's it. Looking at 85, same type of deal. So this is telling me to take the cube root of 8. So now you're asking yourself, what to the power of 3 gives me 8? That would be a 2. Okay. I have one more example like this, and then we're going to look at what happens if my numerator is something other than a 1. So right now we're just focusing on if the numerator is a 1. In a moment, we'll see what happens if it's not. So right here, this is going to be the cube root of 27, which is 3, because 3 to the power of 3 would be 27. All right, so then now what we're going to do here is, let me scroll up so we can see this all at once. Oops. Okay, so now what we're going to do is we're going to see some examples where uh, my fraction right here, my numerator is going to be something other than a 1. So the denominator still is your index. That's never going to change. Then what happens is the numerator is going to become your power. The power can either go afterwards or it can go directly with the base. It can go directly with the base if you want. For for our particular examples, this is going to be the best way that we can do it right here. But I just circled right here. This is the way we're going to do it. Sometimes it can be to your advantage to do it this other way, but no, I don't think we're going to run into any cases like that. Okay, but just be aware that you can move that exponent to the inside if you really wanted to. But for our examples, we're going to keep it on the outside. All right, so coming down here. Okay, so looking at 87, so the denominators tell me that I'm going to do a cube root of 125, and then the numerators tell me to square it afterwards. So just focus on here. So the cube root of 125, so basically what to the third power gives you 125, and that will be a 5, and then you have to square it. So that's what this is. The cube root of 125 is 5. Then we square it, which is 25, and there we go. That's our answer. Okay, 89, yeah, we got to throw a negative in there, make it fun. So on this one here, what you need to remember is negative exponents mean that you take the reciprocal. So this will become 1 over 32 raised to the positive 4/5 power, okay? That doesn't cause anything to become negative. It just causes you to do a reciprocal, okay? So then what we're going to do here is the denominator is a 5, so I'm going to have to do a fifth root. We haven't had to do any fifth roots, but it shouldn't give us too much trouble. Sorry. All these are going to be perfect roots, so we're not really going to get anything crazy. So this shouldn't really cause us any issues, okay? So I know that this is going to come out to a nice number, and it's going to be a 2, and I'll show you why. So 2 times 2 times 2 times 2 times 2. If you multiply that together, let's see, 4, 4, and then you have a 2. 4 times 4 is 16. 16 times 2 is 32. So basically what that's telling me is that 32 is the same thing as 2 to the power of 5, okay? And so that's, when I take the fifth root of this, it's going to nullify the power of 5, and I'm just going to be left with a 2. So I get 1 over 2, and I do have that power of 4, though, left. So I do need to raise this to the power of 4. So basically, if you look here, you're just looking at this part of it. So 4 times 4, so 2 times 2, 2 times 2, I get 4 times 4, 16. So this is going to become 1 over 16. So the 16, it has to be in the denominator spot. It has to be 1 over 16, okay? All right, so our last slide, here we go. Okay, so this is what we're going to do now is throw some variables in there with these rational exponents. This can get pretty let's say tedious, okay, but I kept them pretty simple though. We're not, there's no need for us to go crazy on these. So this is kind of more of an introduction. Basically what we're going to do here is you've got your rules for properties of exponents. That's back from our last unit, actually, from unit 2. Basically, if you're multiplying like bases, you add the exponents. If you're dividing them, you subtract them. If you have power to a power, you multiply, and then you should know these other ones that if you have a power on the outside of a parentheses, whether it's multiplication or division, that power will apply to everything inside there, okay? So what we're going to do here, what I want you to realize here is that C7 and x to the 1/3, they're not attached to each other, and 2 times x to the 1/4, everything's just kind of on its own, and we can do the commutative property and move some things around. So what I can do is I can put the 7 times 2 next to each other, and then I have the x to the 1/3, and I have the x to the 1/4 right here. So what I'm going to do here is I'll go ahead and multiply the 7 times 2, and then when I multiply the like bases, I need to add those exponents, okay? And I'm going to go ahead and write it up here so I have some more room to work on this. So let's see, 7 times 2 is 14. Then I'm going to have x to the 1/3 plus 1/4. Okay, that's what you do. You add exponents when you multiply like bases. So I'm going to have to get an LCD. And my LCD should be pretty simple. It's just a 12. Okay, so I'm going to have to multiply this one by 4 over 4. And the other one by 3 over 3. And that should get me my LCD. So let's see, 14x, this is going to be to the 4/12 plus 3/12. And then we can go ahead and we have that common denominator, so we can add the 4 and the 3 together. So my final answer is 14x to the 7/12. And that's my answer. That's it, okay? I'm not saying it's super easy, but it's not that bad, okay? You just got to remember your properties of exponent rules. So I just have a couple more of these. Let's see. So I've got one with division, and I got one with the power to a power. And then the very last thing we're going to talk about is how to work around those negative square roots. Okay. So looking at 93, so you can break this up. So let's see, 20 divided by 5 is a 4, right? 20 divided by 5 is 4. Now, when I look at the like bases, the common bases, what I'm going to do here is do subtraction. So I'm going to have x to the 1/2 minus 1/4. Once again, I have to get an LCD. This time it's just going to be a 4. It's just 4. So I'm going to multiply just the first one by 2 over 2. So now I get 4x raised to 2 over 4 minus 1/4. And then I can go ahead and do that. I can do the 2 minus 1. So I end up with 4x raised to the 1/4. All right, the last one is fairly simple because it's power to power. You're just going to multiply. So I have x to the 2/3, and then you're going to multiply it by 3, but I'll put that 3 over 1 like that. And basically all that's going to happen here is the 3's will cancel each other out. And you're left with 2 over 1, or just basically x squared. Just x squared. Okay, so power to a power, you multiply. So these were fairly basic, to be honest. They can get very messy, but it just wasn't necessary for what we're trying to do when preparing for our college algebra portion of the course. So we decided to kind of keep this fairly basic here. All right. So the last part we're going to talk about, and so when you're doing your homework, I know a lot of times students are, they see the square root of -25 and you want to say not real. And that's completely true. It's not real. But now we're going to talk about these things called imaginary numbers. Okay, and you're like, imaginary numbers? What the heck is going on, right? Well, imaginary numbers, also known as, complex numbers, okay, they were something that were developed, around 500 years ago. Um, there was a big argument about, if these numbers were relevant or not, right? And so one of the mathematicians is quoted as saying that it's hard to imagine these numbers are not relevant, right? And so it turns out he was correct. And so that kind of got the coin imaginary numbers because you couldn't imagine these numbers wouldn't be important. So it's not like imaginary like they're made up or anything like that. They just got coined that phrase, but they're more known as being complex numbers, okay? And there's courses you can take that are devoted to complex numbers. You could take a full semester course on complex numbers. And so I'm not going to act like I know all about this, but I know that they're used in the field of electricity. Apparently, electrical currents, they use the complex numbers for that phenomenon of electrical current. And so if you're going to go into that field, like electrical engineering or something like that, you'll probably take more courses on complex numbers. Okay? All right, so, but we're going to be very basic here. We're going to be very basic here. And what we're going to do here is if you have the square root of a negative number, it turns into an I. Okay? Now, um, the negative, just the negative part turns into an I. So like on 25, yes, that negative part, that will become I, but you still have the square root of 25. Okay? You still have the square root of 25, and the square root of 25 is 5, so your answer is 5, and then we'd like to put the I on the back side like that, so 5I, okay? And that's really all you really have to know about this. And so what is kind of interesting is that I to the power of 2 turns back into -1 because, if you were to square both sides, right? So that's kind of an interesting thing that maybe we'll look at a little bit closer later on down the road. But for right now, all you need to be successful is to know this. If you square root a negative number, an I comes along with it. That's it. Okay? So on number 2 right here, you're square rooting -5. That will become an I on the outside, and then you're left with square root of. Now it's a positive 5 inside. Now square root of 5, I can't do anything about that. So that is my answer for number 2. That's it. Okay? Like I said, don't overthink it. All right, so on number 3 right here, your negative, we'll pull that out as I, and you're left with square root of 48. Now 48, we can break that down. We can break that down. Remember our perfect squares are, let's see, were they 4, 9, 16, 25, 36, and so on. And so I believe 48 is divisible by 16. So we're going to break that up into the square root of 16 times the square root of 3. Now we can square root 16, so that'll give us I times 4 times the square root of 3. And that answer is great. If you want to leave it like that, that's fine. But traditionally, what we'll do is looks a little bit nicer if we write 4I and then the square root of 3 like that. Square root always goes on the back end. You don't want to put the I back there because it might look like the I is part of the square root. Technically, it's not wrong, but just like I said, this is the traditional format right here. Okay, one left. One left, pretty similar to number 3. So we'll start by dealing with our negative. That will be pulled out as an I, and then we'll be left with the square root of 150. And it looks like 25 can divide into 150. So that's what we'll do here. So we'll have I times the square root of 25, and then times, let's see, the square root of 6. And so we can square root 25. So we're going to have I times 5 times the square root of 6. And then we'll clean that up and write it as 5I square root of 6. Okay? Okay, so when you're doing your homework, I know up to this point you would say non-real, non-real, and so on. Just make sure you read the directions carefully. The directions will indicate if they want you to use I as part of your answer. It will actually say that. It'll say, if necessary, use, I for your imaginary solution or whatever, okay? Um, all right, so that does it for Unit 3. So once we're done here, we're starting our college algebra. So we'll start back at Unit 1 with college algebra, all right? If y'all have questions or concerns, make sure you send me an email so we can address those as soon as possible.